All right, so first I do the force diagram here, making sure my forces are there. Then I go to some of the force statements. In the y, I'm assuming it's 0. In the x, I actually don't know if it's 0 or not. So that's why I'm going to put MA. I'm not sure. So I'm going to say FA minus FF is equal to MA. And I'm going to say FN minus FG is equal to 0. Real quickly, I want to call your attention to FG. Notice that FG there has what sign? Negative. So also notice that this term, mathematical term sum, what does that mean? It means add up. So if I put a minus sign here, that means I'm actually adding a negative value, yes? Which means I've already counted for gravity being negative. So if we go into some algebraic sort of gobbledygook down here, we don't have to insert negative 10 for gravity. We can just make, so I can just say that G is 10. And I've already used the vector to determine which way that's oriented, all right? So the diagram did it for me, okay? And the vector orientation and the sum of the forces. So then here, I will say A is equal to FA minus, and FF is mu F sub n all over m. And then up here, Fn is equal to Fg. And Fg is equal to mass times gravity. So then, in order for me not to squat down and do this problem, Fa minus mu, and remember, Fn is equal to that, so I can substitute mg over m.
Wait,
Yeah.
why is it mu of Fn not F?
Take this, mu is ff over Fn, and solve it for ff. And it becomes mu f sub n. Okay, that's fine. Good question, good question. So we say 25 newtons here, minus mu, which was what, 0.8? 0.8 times the mass, which was 5 kilograms, I think, times gravity. I'm just going to use 10. Shouldn't be too sloppy. Meters per second squared. And then notice that's going to give me newtons, right? See that? Kilogram meters per second squared. And then I'm dividing it all by the mass, which is 5 kilograms. So then that's going to leave me with an acceleration. So this times that is 8, times that is 40. And then that makes negative 15 over that. So that's minus 3 meters per second squared. So the acceleration caused by friction is negative 3 meters per second squared. And what does that tell me? And this is being recorded, so I will post it. So if you miss it, you can get it then. What does that tell me about what's happening with this box? It's going to do what? Yeah, the acceleration means it's going negative. But what does that mean about, like, what is true about friction, which we talked about yesterday? I'm sorry, say that again, Stephen? Friction is a reaction force, and I think Danny or somebody over here just said, who was it? I don't know. Said that friction is stronger. If friction is stronger, what happens? This thing didn't move. See, so you can't just get negative 3 and go, woohoo, negative 3. So I'm going to say it's minus 15 meters per second squared. Or meters per second. Yeah, question? Yeah.
So if, but then.
I'm sorry, please.
So whenever acceleration is negative, v equals 0.
Okay, so the question, sorry, what was your name? Hillary, okay, sorry, Hillary. Hillary had a great question. She said, so does that mean when acceleration is negative, it doesn't move? Which of the pedals in your car gives you a negative acceleration but will never move you backwards? The brakes. You see what I'm saying? Right? Let's say that I had a car and I had a super incredibly awesomely durable transmission and I have no brakes. So my transmission is indestructible. The transmission is the gears, right? Indestructible. But I have no brakes. How do I stop?
You jump out.
Jump out?
Oh, you move the car around.
Stick it in reverse. Because which way are the tires going to spin? Backwards. So if I'm going forwards, I put it in reverse, and then the wheels are going to spin backwards and slow me down. But if I keep on the gas, what's going to happen? Yeah, once I stop, then I'm going to start going backwards now. Right? That's not a real situation. But that's what would happen, Hillary, if this was like the transmission of your car. If this backwards force pushing this way was not a reaction force, then this thing would start moving to the left. But because friction and what other force did I mention yesterday that's a reaction force? Normal force, remember? Because gravity pulls on you. Gravity does, but normal force only pushes up with what you need, right? So normal force and frictional force are reaction forces. They only give you what you need. And you could do this on a quick calculation if we did this. Let's say F sub F is equal to mu F sub N, which is equal to mu mg. Well, I know everything. So mu mg is 0.8 is 40 newtons. How much force is pushing forward? 25. So is this thing going to move? No. See, you can do it like that. Now, what happens if this gets to 40 newtons? Will it move yet? No. Oh, good response. It will not move yet. You must overcome the 40 to get it moving. Okay? So if I go 40, if I go to 41, now I'm going to get it moving. And if I go to 41, if I want to make it so that it has a constant velocity, no acceleration, what do I have to drop the force back down to? If I'm at 41, it starts moving, but I don't want it to accelerate. I want to do a constant velocity. What do I have to drop the force back down to? 40. Because what force overcomes friction? Just 40. So now, if I do that, then I get it moving, go back down to 40, and now it's just going to move at a constant velocity across the table.
So you have to decrease it by 1.
Yes, I would have to go down. If I stay at 41, then what do I have in the right direction? Yes, I have a net force of 1 Newton. So my net force of 1 Newton will produce an acceleration of 0.2 meters per second squared. And assuming that I have an infinitely long thing, I could get this thing up to the speed of light if I wanted. Okay.
Can you explain that one?
About the 40 and stuff?
Yeah.
Okay. So let's say we put this box on the table, and then we say, here, Shirley, pull this. Okay. And then you start pulling. You're like, wow, it's not moving. So you pull harder and harder. And then on the box or in the string or something, we have like, I don't know, like a little dial, right? And then that dial is marked 40. So you pull, and then that dial goes up, 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 up. And if you don't hit 40, it doesn't move, right? But if you hit 40, and then it's still not going to move. If you hit 41, boom, this is going to slide, right? And then if you want to make that thing go at a constant velocity, then you have to drop back down to 40. Otherwise, if you stay at 41, you're going to accelerate that way.
Wait, but I thought when it hits 40, it won't move. Why would we drop it back to 40?
When it hits 40, it won't change. It's not that it won't move. It's that it won't change. So if I hit 40, what's it doing right now before I hit 40? Yeah, it's not moving. So if I hit 40, it won't change, right? You see? Because what was it doing before? But if I do 41, now what's this doing? Moving. So if I don't want it to change, I got to drop back down to 40. But it's still moving.
Oh, I get it. I get it.
Okay, questions? Yeah.
How long would it take before you turn it back to 40? Like, is there a certain?
Oh, I don't know. That's just that's just a purely imaginary thing.
Okay.
Yeah. You've seen this. I know you've seen this. You've probably experienced this. How many of you ever moved furniture across carpet? Okay. Once you get it moving, what is true? Yeah, it's easier to keep moving. That is actually something. That's the difference between F sub k and F sub S. This is, ooh, nice, kinetic and static. This was in the book, I think, right? Friction. Kinetic and static friction. Kinetic friction is friction of things in motion. Static friction is friction of things that are stationary. Okay? Think about this now. You just moved your dresser. You look down on the carpet. What do you see? Yeah, like a bunch of dog hair or whatever. Exactly. You see an indentation into the carpet. That's why it was harder to move. Because when it sat there for a long time, it compressed the carpet and fit in. Your surfaces of everything, this desk, anything, the smoothest thing that you can think of, if you zoom in on an atomic level, that surface is not like this, it's actually like this. And when those things bounce across each other, like if you do this with your knuckles, don't do this, you might rub your knuckles raw. But if you do this, like they just bounce across each other. But if you push them into each other and then try to move them across, now it's harder. Right? Do you get what I'm saying? Right? If you stay light and bounce them across the top, they just kind of skip off each other. That's what happens with kinetic friction. The molecules are bouncing off the top of each other. But if you stop and let them settle, now you have to do static friction. And this is almost always bigger than that. So it's kind of like, remember chemistry, activation energy? It's kind of like that. You have to get up over the hump, and then you can get the thing going. And like I said, you already know physics, because you've moved furniture. You've moved something on carpet, and you know what that's like. Once you get it moving, keep it moving. Because if it stops, oh crap, then you're going to do the whole thing again.
So static friction is like bigger than kinetic friction in terms of value?
No, this static, yes. Static friction is always bigger. So for example, mu sub k for an object might be 0.3. Mu sub s for that same thing might be 0.35. This is an example. This is not true everywhere.
Would they ever be equal?
I can't think off the top of my head of anything where that's equal. Okay? All right, so everybody okay with this? When do you guys need to leave? Oh, okay, whatever. Those people who are club fairing it up, leave when you need to leave. I'm not going to keep track of it. How are we doing? Questions? Questions? Yeah.
About the acceleration, why are you using
Right here? Okay. So just asks an interesting question. It's like, you watch me do this, and you're like, okay, whatever, I believe you, right? You're supposed to be the teacher. So you tell us this is how you do it. I see how you do it. It means nothing to me. Okay, let's take a step back and look at everything from a certain perspective. Is everybody here clear on the force diagram right here? I think that's reasonable, right? Like we all get it. It's like gravity goes down. It's not going through the table, so something must be pushing up, right? Because for reaction, there's equal opposite reaction. So this is no problem. Do you understand the basic force statements? Does that make sense? Yeah, so for example, if you look at a tug of war thing, okay, like let's say we're going to go watch the Super Bowl of tug of war, and we watch two teams practicing, and the red team hooks a rope to a big truck that's just parked in the parking lot, and whoop, they drag it along the parking lot. And the blue team hooks it to the same truck, and they can't really move it. Who's going to win the tug of war? See, you all know this instantly because you already understand physics. You understand that the bigger force is going to win. You understand that when you take the bigger force and you subtract the smaller force, there's a leftover force, which means the red team is going to pull the blue team towards them. Does this make sense? So that's what's happening here. It's just happening in 2 dimensions. Think of these arrows as tug of wars. So what I'm saying is that the tug of war in the vertical direction, in the X and the Y dimension, is a tie. And in a tug of war tie, what happens? Nothing. Nothing happens. They just stay there. But in a horizontal tie, in an X, no, sorry, not a tie, but in the X direction, right? What did I assume would win? Yeah. Just by the way I set this up, I assumed that this would win. So I put 25 FA minus FF. Was I right? No. Ah, see, those sneaky blue people were in the parking lot just kind of going half speed. They were trying to fool the red team because when it came down to the competition, boom, FF, the blue team won, right? But so that's what's going on here. You see, the nice thing is it doesn't matter which direction you pick as positive. The math takes care of it. Because we assumed that this would be the winning direction. But it turns out that left is the winning dimension. Now, we have to add a little curveball, right? And that curveball is, what types of forces are these two? This is an action force, but this is a reaction force. So, can you tell me this? If I'm this guy pulling 25 newtons, can you tell me exactly how much friction is pulling? How much is friction pulling? Here's this, that's that thing. I'm pulling 25 newtons. How much is friction pulling back? 25. Is everybody cool with this? Does that make sense?
So that makes it stationary.
Yes, it stays stationary because, remember, what was it doing before I pulled on it? Nothing. So if friction matches this force, it stays the same, which means it stays stationary. Questions? Yeah. Oh,
So
first
that
one.
when we write those equations,
Uh-huh.
are they just like assumptions?
Yes.
Okay. Wait, another question. So sigma f of x equals ma, is that always true?
If it's not true, then the math will show me that. And that's what happened here, right? I assumed that A was positive and it would move this way. But it just so happens that it turns out that A is negative value moving this way. And now I have to combine the math with the logic that says, wait a minute, this is a reaction force, so it can't accelerate this to the left, so it just doesn't move. Okay, then Justin, then back to you.
For the f of a of the 100 sigma fx, so f of a minus f of f, like I thought, since there's nothing pulling back on it, I immediately thought 0. So I thought f of a equals ma. That's, you added the mu and that's where I got the.
Okay, so does this make sense that you're pulling right to the right, and friction's pulling to the left? So when you did this, you didn't include friction, or?
No, I just put 0. Like, I immediately thought, I didn't realize that it was friction. Because I thought for some reason it's smooth surface.
Okay, so if I write smooth, then you can assume that, okay? If I don't write smooth, don't assume it. And here's the thing, remember, being the person that I am, making mistakes every once in a while, if you think it should be, or if you thought I was gonna make it smooth, does it hurt to ask? See, that's one thing in college that's very, very helpful. It never hurts to ask a question during a test. Excuse me, is this what you meant by this question? Because I'm not quite sure what you're trying to say. That's like putting the test questions in a way that are clear is not your responsibility, that's your teacher's responsibility. So if it's not clear to you, say so. Because if you ask me a question that I think gives away the answer, what's the worst thing I have to do? Well, no, if you ask me a question that I can't answer, the worst thing I have to do is say, I can't answer that. Or if you ask me a question that I think should be understood, and I look at it and I say, okay, I see what you're saying, but you should know that. For example, if you said, I don't know what f sub f is equal, what can I do? Then I would say, well, you should know that. You should have written it on your formula sheet. Did you guys already do that? Okay, so, all right, we're gonna do some more of this tomorrow. She needs to borrow this for a minute, so my board's gonna die. Rip. But we will do more of this tomorrow. Yeah. Oh, yeah, good gravy. I've been recording for like 18 minutes.